Welcome back to another video. Today I'll be going over the practice final for spring of 21. Starting out with number 1, we have a transfer function problem. So what we want to do is find the ratio between VO. We want to find VO over IS. All right, there's a couple different ways you can do this. What I chose to do is do current division and then Ohm's law on that to find the VO over IS. All right, to get started, we want to redraw our circuit in terms of the components are going to be with S. I forget what that actually means, but we keep our source the same. We are going to keep the resistors the same. Actually, I'll redraw this with the actual components. Okay, so 5 ohms, that means it's just a simple resistor. 8 henries, that means it's going to be an inductor. 4 farads is going to be a capacitor, and then 3 ohms is a resistor. So this stays as 3, and this still stays at 5. But for an inductor, it's going to be 8S because it's going to be L times J omega, and J omega is S. And same thing with the capacitor. This is going to be 1 over 4S because the capacitor is 1 over J omega C. And this becomes S. All right. Now with that, we have our circuit redrawn. We can now start solving for VO over IS. So to get started, what I did is to find this current called I1. It's an arbitrary current that I just assigned just to make my life easier. So what I first started doing is doing current division to solve for I1. So I1 is going to be equal to IS times, probably need a bigger parenthesis than that, IS times, and we're going to use the other series components, so it's going to be 5 plus 8S, and that's all going to be over all of the components added together. So 1 over 4S plus 3 plus 5 plus 8S. Okie dokie. Now with that, I'm going to do some simple algebra. To get this 4S out of the denominator, I'm going to multiply this by 4S over 4S, and then you just multiply through. So this would be equal to IS times, I'm actually going to keep this 4S in the numerator without distributing, but I'm going to distribute the denominator. So we're going to have 1 plus 3 plus 5 is 8 times 4S is 32S. 8S times 4S is equal to 32S squared. All right, so now that we have that, we can now solve for VO. With VO, we're just going to do simply Ohm's law. Since we have the current, we can just do Ohm's law. So VO is going to be equal to I1 times 1 over 4S. Okay? We know what I1 is. It's just going to be this. So I1 is going to be equal to IS, or VO is going to be equal to IS times 5 plus 8, that looks like an S, 5 plus 8S times 4S all over 32s squared plus 32s plus 1, and all that times 1 over 4s. And this is why I kept the 4s in the numerator, because that now this 4s and this 4s, they cancel out. And what we also do is divide is over to this side. So with that in mind, we now can have our transfer function. So h of s is going to be equal to VO over IS, and that's just simply going to be equal to 5 plus 8s all over 32s squared plus 32s plus 1. And boom, there is part A already done. Okay then, now we want to solve for part B, which asks us to find the zeros and the poles of our transfer function. To do that, part B, finding the zeros and poles are just really simple. So to find the zeros, you take the numerator and you set it equal to 0. So zeros is going to be 5 plus 8s is equal to 0. So that means s is going to be equal to minus 5 over 8. And I think that's it's equal to negative 0.625. I might want to check my work on that, but I think that's it. Okie dokie. And now to solve for the poles, there's probably a few different ways you can solve for the poles. The easiest way is just do the quadratic formula. So we're going to have the opposite of b, which is 32, plus or minus the square root of b squared, so 32 squared, minus 4 times 32 times c. And this is over 2 times 32. All right. And after doing that in your calculator, you find you have two poles at negative 0.9677 and another pole at negative 0.0323. And now the problem asks us to find what the value of our transfer function when omega is equal to 0. So when omega is equal to 0, that means we have a DC circuit. So if you remember back in circuit theory 1, a capacitor acts like an open circuit when in DC conditions, and an inductor acts like a short circuit. So you can just simply see with your circuit theory 1 laws is that we're going just to have an equivalent circuit of 5 ohms because there's going to be no current coming this way. But you can also prove this by looking at the transfer function, and that's how I'll do it for you. Oh, crap. C is asking us to find when omega is equal to infinity. And with infinity, I find the easiest way is just to plug it in. So when you're finding h of s of infinity, infinity is a pretty big number. So that means you don't really do count for the 5 and the plus 1 because it's just going to be so huge that the plus 5 or plus 1 doesn't really do anything to infinity. So what I do is just plug in infinity for all of our s's. So this is going to be infinity over infinity squared plus infinity. And we can definitely see that our denominator is going to increase a lot faster than our numerator, and that means as the limit goes to infinity, we go equal to 0 because the denominator is going to get lower and lower and lower and lower, or higher and higher and higher. All right, now D is asking us to find when when omega is 0. And so you just plug in all the numbers. So you have 5 plus 8 times 0 all over 32 times 0 squared plus 32 times 0 plus 1. And this is equal to 5 over 1, which is equal to 5. Here is our second problem. It is a mutual inductance problem. So with mutual inductance, that means that these two inductors, they are acting on each other, and you have to introduce a dependent source into your equation or into the circuit. So first, what we want to do is to define a current flowing through this inductor. Okay? So what I did is that I made my current pointing down, and I just named it Ix. And we can easily define Ix by using our mesh currents. So I1 goes down, and then I2 goes up, so that means I2 is going to be resisting the current in this wire. All right? And the problem is asking us to solve for the mesh currents. Okay? So now what we want to do is, since I drew my current flowing down, that means we have positive dot convention. So that means we're going to have voltage drops across or along that dependent sources we introduce. So now I'm going to redraw the circuit so we can have those dependent sources inside our circuit. Now that the circuit has been redrawn, we now need to define our sources. So like what I just stated is that I have positive dot convention because they're both entering on the dots. So with that in mind, so we have Ix flowing downwards. So that means I have a voltage drop right here. And what that value is going to be actually is going to be J9, the mutual inductance, times I3, the current of the other inductor, times I3. All right? And now what we want to do is do this dependent source, and the current is flowing up, but it's still positive dot convention, so that means we have plus minus like that. And the value of that current, or that voltage, I mean, is going to be 9J, and it's going to be multiplied the current of the other inductor, which we defined as Ix, which is equal to I1 minus I2. And actually, can I fit it? I1 minus I2. Yeah, I'll just put it on the outside. I1 minus I2. And now we have everything set up in order to solve for our mesh currents. Now it's time to solve for our mesh currents. I'm going to start with I1. So we're doing Kvl I1. All right. And that's just simply going to be equal to 3J times I1. So 3J I1. And that's going to be plus with the voltage drop, so it's J9, 9J I3, and then it's going to be plus J23 times I1 minus I2. J23 times I1 minus I2, and that's all going to be equal to 21 with a phase angle of 169 degrees. All right, and now we can simplify this. So we're going to have I1 times 26. No. Hold on. Oh, I wrote this down wrong. I am so sorry. This is supposed to be 18. Yes. Okay. So instead of this being J23, this is supposed to be 18. Yes, okay, I was right. All right, so now that's going to be equal to 3j plus 18. J is 21j, and now plus I2, which is going to be equal to negative 18j. And then we're going to have plus 9j I3 is equal to 21 phase angle 169 degrees. All right, and now we do KVL I2, and we just go around the loop. So I'm going to start at top, so it's going to be negative 9j I2 plus 10 I2 plus J18 times I2 minus I1, and that's going to be minus 9j I3 is equal to 0. So I1 is just going to be negative J18 plus I2, which is going to be 10 plus 18 minus 9 is plus 9j. And then plus I3 is going to be negative 9j is equal to 0. And now our final KVL loop is going to be I3, and it's pretty simple. So it's going to be 13 I3 plus J11 I3 plus 9j I1 minus I2 equals 0. So then we have I1 is going to be equal to 9j plus I2, which is equal times negative 9j plus I3 times 13 plus 11j is all equal to 0. And there are your 3 mesh currents. Pretty simple problem since we don't have to do any calculation. Here's our final problem of the practice final. I won't be doing the bonus because Bodhi plots take too much time and I don't feel like doing it. All right, so we have an ideal transformer problem. I should have drawn our dots before. Oh. And so we have a dot right here and a dot right here. So that means we will have negative dot convention. Oh, I'm dropping everything now. Okay. So what we want to do is first to assign our currents and our voltages of these inductors. So I'm going to plus minus V2 and then plus minus V1. All right, now what we're going to do is assign our currents. So we're going to have our current going down of I1 and current going up of I2. You can assign the currents all you want, but doing them this way, current and voltage this way, just kind of makes it easier to detect the positive or negative dot convention for ideal transformers. All right, what else I'm going to do is to manipulate this ratio to make it 1.8 over 12, which is equal to 2 over 3. 2 over 3. So now I can get rid of this. And now we have a dot convention of 2 over 3. I really want that 3 to be in the numerator. All right, so now the problem wants us to make a system of equations in order to solve for the circuit. All right, so remember the 2 easiest equations is going to be your I1 and I2 and V1 and V2. So first equation V2 over V1 is going to be equal to, since we have negative dot convention, we have negative 2 over 3. Okay? And then we want to do I1 over I2 is going to be equal to negative 2 over 3. So now we have equation 1, equation 2, and now we get to the meat and potatoes of this problem. We have to either choose mesh or nodal analysis. I'm going to go with nodal analysis because mesh looks like it gets a little bit complicated. You can do it, it just looks a little bit complicated in my eyes. All right, so we have a node right here, which is equal to V2. And we have a node right here that is equal to V1. All right. So now what we want to do is create a supernode because we have our ground at the bottom. Since we have ground at the bottom, that means we have to make a supernode because there's a voltage source in between two nodes. So here we go. And all of this up here is a supernode. So our third equation, which can be very simple, is just simply going to be the node voltage of the supernode. So it's going to be, since we have plus to minus, that means V1 is at the higher voltage. So we have V1 minus Vx is equal to, not over, is equal to 4 phase angle negative 69. Nice. There is our third equation. And now our fourth equation is just simply going to be the voltage, or like the Kcl around the supernode. So now Kcl Super Node is just simply going to be, I'll start at V1. So it's going to be equal to, I'm going to assume all of my currents are going away from the super node. So we're going to have I1 plus V1 over negative J21 plus, we come over here, and it's going to be Vx over J9, and then it's going to be minus I2, and that is going to be equal to 0. You can also, instead of I2, it'd just be better to use I2 because we already have this current defined. So since this is series components, I2 is going to be the same throughout this entire series right here. So might as well just use I2 there because we don't really care about being extremely exact. Like you can do Vx minus V2 over negative J21, which is the value of Vx. Actually, no, it's V2. Since our current is coming up in this way, it's going to be V2 minus Vx. But I just use I2 because it'd be simpler putting it into your calculator that way. But you don't have to solve in this problem. So there is our fourth equation. And now our fifth equation is simply just going to be what I2 is, which I just said is going to be V2 minus Vx all over negative J21 is equal to I2. And there is our fifth equation. That is it for this practice final. I think this is one of the more straightforward tests we can probably have as a final. And yeah, good luck.